Equations for simple harmonic motion. Before working through this video, you must know the basic concepts about simple harmonic motion. If you don't, you should refer to the following video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. We have already seen that the projection of uniform circular motion on a diameter of the circle follows simple harmonic motion, and we will use this fact to obtain the equations for simple harmonic motion. Let us consider an object traveling in a circle. The projection of this motion is a simple harmonic motion, and the object appears to be moving back and forth with an amplitude equal to the radius of the circle. The object is rotating around the circle with a constant angular speed. At time t equals 0, the radius is horizontal, and at time t it has moved through an angle theta radians. The displacement of the object is given as follows. From our previous study of circular motion, we know that the angular speed is constant, and rearranging gives theta is equal to angular speed times t. Replacing theta with angular speed times t, we get the equation of the position as a function of time for an object in simple harmonic motion. Let's see how it works. Pay attention in this question. First of all, we need to write down the equation given the displacement. We have been given frequency, so the angular frequency or angular speed can be found from our previous study of circular motion. We also have an amplitude equals to 4 millimeters. So we can write the equation for displacement. We now replace t with 0.5 to get the displacement required by the question. We can find the velocity of an object doing simple harmonic motion in the same way that we determined its position. First, find the velocity of the object, then take its x component. The result of this calculation will be the velocity as a function of time for simple harmonic motion. To begin, recall that the velocity is tangential to the object's circular path and has a magnitude equal to angular speed times radius. Replace cosine of 90 degrees minus theta with sine of theta. Then replace theta with angular speed times t. So the horizontal component of the velocity is given as follows. Let's see how it works. Pay attention to this question. The block is released from rest 11 centimeters from its equilibrium position, which means its maximum displacement is 11 centimeters. That is, the amplitude is 11 centimeters. We already know to calculate the period from the mass spring system, and when we compare these two expressions, we conclude the angular speed is the square root of spring constant divided by mass. We need to write down the equation given the velocity. We now replace t with 1.5 seconds and perform the calculations. We can find the acceleration of an object doing simple harmonic motion in the same way that we determined its velocity. Find the acceleration of the object, then take its x component. To begin, recall that the acceleration is toward the center of the circular path. This is the centripetal acceleration. We now take the x component of this acceleration. The equation of the acceleration as a function of time for a body in simple harmonic motion is we have just found the following sets of equations for simple harmonic motion. We now will use the relationship between circular motion and simple harmonic motion to show important features of the simple harmonic motion. Consider the mass spring system. Now suppose a body is oscillating with simple harmonic motion starting from a position of maximum positive displacement. Then its displacement, velocity and acceleration at any given time t can be found from the following equations. We have to put a minus sign in the second equation for velocity because the system is moving back toward the equilibrium point, so the velocity is negative. We also have to put the minus sign in the equation for acceleration because the acceleration is always directed towards the equilibrium position. We can see that when the mass is at its maximum or minimum value of x, its velocity is zero, and the acceleration has maximum magnitude. In these two positions, theta is equal to 0 radians or pi radians. Pay attention in the next figure, when the mass is at the equilibrium position of the spring. Here the speed has its maximum value, and the acceleration is 0. In this position, theta is equal to pi divided by 2, or 3 pi divided by 2. When the particle is moving rightward through the equilibrium position, its velocity is positive and the magnitude is at this greatest value. When it is moving leftward through the equilibrium position, its velocity is negative and the magnitude is again at this greatest value. The acceleration magnitude is 0 when the cosine is 0, which is when the particle is at the equilibrium position. And the acceleration magnitude is maximum when the cosine magnitude is maximum, which is when the particle is at an extreme point where it has been slowed to a stop so that its motion can be reversed. Indeed, comparing the equation for displacement and the equation for acceleration, we see an extremely neat relationship. In simple harmonic motion, the acceleration is proportional to displacement x but opposite in sign, and the two quantities are related by the square of the angular speed. This is the hallmark of simple harmonic motion. The particle's acceleration is always opposite its displacement, hence the minus sign, and the two quantities are always related by a constant angular speed squared. Whenever you see such a relationship in an oscillating situation, you can immediately say that the motion is simple harmonic motion and immediately identify the angular frequency of the motion. In a nutshell, in simple harmonic motion, the acceleration is proportional to the displacement x but opposite in sign, and the two quantities are related by the square of the angular speed. We will deduce an equation for finding the velocity at a particular position when you know the amplitude and period, but you don't know the time being considered. Let us write the equation for velocity. We now take the most important trigonometric identity. Rearranging the equation, we get a new equation for velocity. Let's see how it works. Pay attention in this question. The period is read off the graph as t is equal to 0.2 seconds. Since angular speed is 2 pi divided by period, we get the angular speed. The maximum velocity is then angular speed times the amplitude, and the amplitude is taken from the graph. The maximum acceleration is found from the equation above. The velocity at 1.5 centimeters is found from the equation above for velocity.